Weather theory for pilots is intended to bridge the gap between basic weather training and technical academic programs and assist pilots in their operational understanding and application of aviation weather theory and technologies.
You'll notice throughout the block we've borrowed illustrations by Robert Osborne taken from AC 006A Aviation Weather. As Oscar Wilde said, imitation is the sincerest form of flattery.
Sometimes we take ourselves a little too seriously, so we've poked some fun at ourselves and others. We'll include various case studies. These incidents are not intended to disparage or malign any individual, group, or organization. Their sole purpose is illustration.
The series was compiled by Terry Langford and narrated by Terry and Gay Langford. Send comments, suggestions, or questions to the address shown. We greatly acknowledge the assistance of the National Weather Association's Aviation Meteorology Committee and the pilot, controllers, and forecasters who contributed to the creation of this program.
Although weather affects a pilot's flying activity more than any other physical factor, most pilots agree that weather is the most difficult and least understood subject in the training curriculum. Surveys indicate that many pilots, including instructors, are uneasy with or even intimidated by weather. In spite of these facts, or maybe because of them, weather training for pilots typically consists of bare bones, while weather-related accidents remain relatively unchanged. Along with advances in weather observations, such as satellite, radar, and the proliferation of surface reports, there is no doubt that there has been a significant improvement in forecast accuracy and weather dissemination. Report after report, both government and industry, have recommended improved weather education for pilots, dispatchers, and controllers. Unfortunately, little has filtered down to the operational level. Of all general aviation accidents, over 1/4 involved the weather. Of these, almost 1/3 resulted in fatalities. Part of the problem lies with the fact that weather training provides little in the way of practical application. Why? Most aviation weather training does not relate theory to the real world. Pilots are simply required to memorize a series of unrelated, often oversimplified facts to pass written and practical tests. The most dangerous scenario remains continued VFR flight into instrument meteorological conditions. Over 2/3 of these accidents resulted in fatalities. Almost 3/4 of the pilots involved did not have an instrument rating. Ironically, the overwhelming majority had over 1,000 hours, and more than 1/4 were instrument rated. Attempting to depart the Los Angeles basin under an extensive overcast, this pilot ran out of VFR and options all at the same time. Trapped in a box canyon, the pilot crashed the airplane on an almost 45-degree slope. The only positive aspect of this accident was that the pilot and passengers escaped serious injury. Oversimplification. Sir William Napier Shaw's Manual of Meteorology, published in the late 1920s, nicely sums it up. Every theory of the course of events in nature is necessarily based on some process of simplification of the phenomena, and is to some extent, therefore, a fairy tale. Watch out for absolutes. Weather is dynamic. There are few, if any, never, or always, when it comes to the weather. Take, for example, the written test question, what is the approximate base of the cumulus clouds if the surface air temperature at 1,000 feet MSL is 70 degrees Fahrenheit and the dew point is 48 degrees Fahrenheit? The question asks the applicant to calculate cloud bases from surface temperature and dew point based on lapse rate. The result is only an approximation for one specific set of circumstances: convective clouds produced by surface heating. A national aviation publication once touted this formula as a means to calculate any cloud base. So what's the solution? To begin, an understanding of 3 basic atmospheric properties explain virtually all weather phenomena and most aviation weather hazards. And yes, some of the theory and explanations we'll discuss are oversimplified, but they do reflect what occurs in nature. There are 3 factors in the weather equation: moisture, vertical motion, and stability. Sound familiar? They should. Abundant moisture, an upward vertical motion producer, and unstable air are the three ingredients required for thunderstorms. Moisture is the first factor in the weather equation. Atmospheric moisture comes in three forms: solid, liquid, and vapor. An air mass can be moist or dry. Moisture can be added or removed. Clouds and precipitation are made up of ice crystals or liquid water. Water vapor is an invisible gas suspended in the air. Moisture accounts for the hazards of low ceilings and many low visibility events, is a component in thunderstorms and icing, and to a minor degree affects density altitude. Vertical motion is the second factor in the weather equation. Upward vertical motion increases relative humidity, clouds, and precipitation. Downward vertical motion decreases relative humidity, evaporates clouds, and precludes precipitation. Vertical motion can result in thunderstorms or clear skies. Atmospheric stability is the third factor in the weather equation. Stability often determines whether the weather is benign or severe, the ride smooth or turbulent, visibility good or poor. Stability basically falls into two categories: stable and unstable. Stable weather systems produce steady, widespread precipitation, poor visibility, and smooth flying conditions. Unstable systems produce showery precipitation, heavy at times, good visibility except in showers, and turbulent flying weather. There are many qualifications to these statements. The following modules provide further explanation of the elements in the weather equation. With a basic understanding of these properties, we can start to apply the theory to our flight environment. Keep in mind the principles presented in the introduction, specifically that of all general aviation accidents, over 1/4 involve the weather. That the most dangerous scenario remains continued VFR flight into instrument meteorological conditions, and the problems of oversimplification and generalizations, and the fact that the air can be moist or dry, produce upward or downward vertical motion, be stable or unstable, or any combination.
Material is intended for the non-meteorologist pilot, dispatcher, weather briefer, and controller. Due to the complex and dynamic nature of weather, some of the theory and explanations are simplified. We've cut some corners on the technical, physical operation of the atmosphere. Some of the graphics and explanations are meteorologically unrealistic. Please forgive us when we exercise a little poetic license. Our goal is to provide a basic knowledge of the terms and phenomena essential for an understanding of aviation weather.
Air does not technically hold water vapor. This analogy helps describe the atmosphere in common, non-academic terms. Condensation may take place prior to the air temperature reaching its dew point, or skies may remain clear. Temperature is a significant factor in determining the amount of water vapor the air can accommodate. Warm air can hold more water vapor than cool air. Any event that cools the air or adds moisture decreases its capacity to hold water vapor. Conversely, any event that warms the air or removes moisture increases its capacity to hold water vapor. Before we continue, we need to define a parcel of air. A parcel is a small volume that retains its composition. It does not mix with the surrounding air. The balloon represents a parcel of air. If the parcel is lifted, it expands from the decrease in pressure and cools. If the parcel descends, it is compressed due to the increase in pressure and warms. We'll expand on this concept in the module on stability. Water vapor in the atmosphere is measured in several ways. Relative humidity is the ratio, expressed as a percentage, of the amount of water vapor present in the air compared to the maximum amount of water vapor the air could hold at its present temperature. Relative humidity depends on both temperature and water vapor. Dew point is the temperature to which the air must be cooled, water vapor remaining constant, to become saturated. Each parcel contains the same amount of moisture. However, the warmer samples have the capacity to hold additional moisture in the form of water vapor. Because of this, the relative humidity of the warmer samples are lower than the cooler samples. All have a dew point of 5 degrees. Therefore, the first sample would have to be cooled by 20 degrees and the second by 10 degrees, other factors remaining constant, to reach saturation. When the air can no longer hold additional water vapor, relative humidity is 100%. Temperature and dew point are equal, the air is saturated. Should any more water vapor be added or the air cooled to a lower temperature, condensation will normally occur in the form of visible moisture. The capacity of the air to hold water vapor is affected primarily by temperature, and the temperature can be affected through several processes. Conduction. Air can be cooled by contact with a cooler surface. This process may result in the formation of fog. Air can also be warmed by contact with a warmer surface. Daytime surface heating causes the low clouds to dissipate. Convection. As air rises, it cools due to expansion. This can result in the formation of clouds. When air descends, it warms by compression. Clouds will tend to dissipate. The actual moisture content of the air can be affected by evaporation and condensation. Evaporation adds water vapor as air moves over a moist surface. As cold air moves over relatively warm water, the water evaporates, adding moisture to the air. Water vapor is removed from the air through the process of condensation. Okay, raindrops aren't green or teardrop shaped. These were in my symbols library. Change of phase is the transition of a substance, in this case water, from one state, gas, liquid, solid, to another. This involves the exchange of heat, known as latent heat. Although the temperature of the environment changes, the temperature of the water undergoing transition remains constant. A source of energy in the atmosphere results from latent heat absorbed or released during change of phase. When water vapor condenses into a liquid, or liquid water freezes, latent heat is released, a prime energy source for thunderstorms. As ice melts or liquid water evaporates, latent heat is absorbed from the environment. Water vapor, a gas, can change directly into ice without going through the liquid phase. This process, deposition, may result in the formation of frost. Ice can sublimate, bypassing the liquid stage. An aircraft with structural ice will lose ice once out of the icing environment, even though the temperature remains below freezing. Condensation, evaporation, freezing, melting, deposition, and sublimation are factors in the weather machine. We will refer to this process in subsequent blocks and modules. No absolutes. This written test question asks what type of weather is most likely with a small and decreasing temperature dew point spread. The best choice is fog or low clouds. Rule of thumb. With a close temperature dew point spread, approximately 3 degrees Celsius, expect fog. Be careful. A close temperature dew point spread is only one factor in the formation of fog. This rule of thumb is an oversimplification, not to be ignored, but to be used with all other available reports and forecasts. We'll discuss this in greater detail in the module on low ceilings and visibilities. How can we determine if an air mass is moist or dry? Low-level moisture can be determined by comparing METAR temperature and dew point. Moisture is implied in satellite and radar observations and weather forecasts. Thunderstorms imply a moist atmosphere. A description of atmospheric moisture is often contained in National Weather Service Office area forecast discussions. Area forecast discussions are available on the Aviation Weather Center and Local Weather Service Forecast Office websites. Local area forecast discussions provide expanded insight into the forecaster's rationale. This example from the San Diego, California office alerts users to the problems of coastal stratus and fog. Stratus and fog along the San Diego County coast early this afternoon expected to regroup and move back inland early this evening and lower overnight. Exact timing uncertain, but expect widespread low IFR conditions to develop with bases 100 to 600 feet MSL and tops at or below 1,000 feet MSL, spreading inland locally 10 to 15 miles by Monday morning. Visibility will likely be at or below 1 mile in mist and fog along the far inland extent of the stratus layer and over higher coastal terrain. Closer to the coast, widespread 3 to 5 mile visibility will be likely overnight, with areas of 1 to 3 miles possible. Mountains, deserts, foothills. Clear skies, unrestricted visibilities. Implies dry air mass. Throughout the series, we'll build on this discussion of atmospheric moisture and its effects on aviation weather. Vertical motion is the second factor in the weather equation. Clouds, weather, and aviation weather hazards are closely related to vertical motion. In the general circulation, comparatively large areas have gradually ascending or descending air. Large bodies of cool air undercut less dense warm air. Large bodies of warm air may override retreating cooler air, forcing the warm air aloft. Air masses may be forced upward by sloping terrain. Vertical motion can be produced, enhanced, or dampened by one or all of the following: convergence, lows, troughs, fronts, dry lines, convection, warm air advection, and upslope. Divergence, highs, ridges, cold air advection, and downslope. Upward vertical motion is cumulative. A surface front supported by an upper trough may produce severe weather. A front moving through an upper ridge may result in little, if any, weather. Downward vertical motion tends to create clear skies and usually smooth flying conditions. No absolutes. Exceptions occur when downward vertical motion traps fog, haze, and smoke near the surface. Widespread areas of IFR can develop within a few thousand feet of the surface. A turbulence hazard can often develop in areas of strong pressure gradient and downslope winds. On surface weather maps, isobars indicate general wind flow patterns. Notice that the flow is out of areas of high pressure, across the isobars, into areas of low pressure. Convergence refers to an inflow or squeezing of the air. Surface convergence occurs in areas of low pressure and along low pressure troughs, an area of elongated low pressure. When moisture is sufficient and convergence is strong enough, condensation occurs. Divergence, the opposite of convergence, refers to an outflow or spreading of the air. Surface divergence occurs in areas of high pressure and along high pressure ridges, an area of elongated high pressure. Surface divergence is a drying, stabilizing process. Convergence results from a narrowing of the isobars. When airflow into an area is greater than the outflow, convergence occurs. Since the ground prevents the air from going down, there is only one way for it to go, up. When airflow out of an area is greater than the inflow, the air diverges. This is indicated by a widening of the isobars. Downward motion, subsidence, causes the air to spread out near the surface. Differences in temperature, humidity, and wind may change rapidly over relatively short distances. As a result of density differences, air masses of different properties don't tend to mix. The less dense air is lifted, producing upward vertical motion. When cold air replaces warm air, it is a cold front. As cool air retreats, warm air overrides and replaces the cool air. This is a warm front. As a cold front overtakes a warm front, an occlusion or occluded front develops. As the name implies, a stationary front has little or no movement. The type and severity of the weather depends on the moisture available and stability of the atmosphere. A dry line or temperature dew point front marks the boundary between warm, moist air from the Gulf of Mexico and hot, dry air from northern Mexico and the southwestern United States. Since the moist air from the Gulf is less dense than the hot, dry desert air, it's forced aloft. If the air mass is unstable and moisture sufficient, thunderstorms develop along the boundary. Dry lines usually develop in New Mexico, Texas, and Oklahoma during the warm season. Different surfaces absorb different amounts of solar radiation. This results in convection produced by uneven heating. Warmer, less dense air rises, replaced by cooler surrounding air. Convective currents continue as long as uneven heating persists. With sufficient moisture, clouds form. These clouds indicate upward vertical motion to the cloud tops. Downward vertical motion occurs in the clear air between the clouds. Expect turbulent conditions, often moderate in intensity, below the cloud tops, and smooth flying conditions above. With abundant moisture and unstable air, convection may be all that's required to initiate thunderstorms. From the surface to about 10,000 feet, warm air advection produces upward vertical motion. As warmer, less dense air moves into an area, it will tend to rise. Warm air advection causes surface pressures to fall. This results in convergence and upward vertical motion. Warm air advection destabilizes the lower atmosphere. Cold air advection results in downward vertical motion. When cooler, denser air moves into an area, it tends to sink. Cold air advection causes surface pressures to rise. This results in divergence and downward vertical motion. Cold air advection tends to stabilize the weather at and near the surface. Orographic describes the effects of terrain, especially mountains. It can be upslope or downslope. Upslope clouds and fog form when air is forced upward, expands, and cools adiabatically. Moisture forced upslope and stable air are favorable conditions for the formation of upslope clouds and fog. Upslope is most prevalent during the cool season in the Midwest, where terrain rises steadily from the Gulf of Mexico to the Rockies, and along the slopes of the Appalachians. Although upslope clouds and weather can occur anytime and anywhere air moves up sloping terrain. Upslope can be widespread and will persist as long as favorable conditions continue. Should the air be unstable, upslope may be all that's required to initiate thunderstorms. Air moving down a slope warms and dries. This accounts for the rain shadow-produced dry, semi-arid regions of the Intermountain region. Other examples are the Santa Ana of Southern California and the Chinook, Native American fur snow eater, along the east slopes of the Rockies. How can we determine areas of vertical motion? With a knowledge of terrain, vertical motion can be inferred from circulation patterns on current and forecast weather charts. Vertical motion producers may be found on National Weather Service Forecast Office area forecast discussions. Examples: marginal VFR to occasionally IFR conditions and generally light snow showers are expected today in association with upper trough passage and cold air advection. Subsidence will slowly erode stratocumulus from the west beginning Saturday. Lingering inverted surface troughing will provide background convergence to support lingering lake effect snow showers through the daytime today. Increase in surface ridging will take hold tonight. Light snow and flurries should come to an end from north to south from this morning as high pressure builds in across the region. Residual moisture ascending the mountains is likely to result in light snow and reduced visibilities across the Appalachians late tonight. The entire region will experience increasingly gusty winds late tonight behind the front. The gusty winds and mountain snow showers should slowly abate Friday afternoon and evening as low pressure over New England pushes away from the area. Like moisture throughout the series, we'll build on this discussion of vertical motion and its effects on aviation weather. The last factor in the weather equation is stability, the capacity of the air to remain in equilibrium, its ability to resist displacement. Recall that a parcel is a small volume that does not mix with the surrounding air. If we lift a parcel by applying an external vertical motion producer, then remove the lifting mechanism, one of several things will occur. If we lift a parcel, then remove the lifting mechanism, the parcel returns to its original position, absolute stability. This occurs when the lifted parcel is cooler, denser than the surrounding air. In the second case, once lifting begins, the parcel continues to rise spontaneously, even though the external lifting mechanism has ceased. Absolute instability. The parcel is warmer, less dense than the surrounding air. Finally, the parcel may initially resist upward displacement when unsaturated, but upon saturation spontaneously continues upward. Conditional instability.
Don't become overly concerned about this discussion of stability. It's background information that will help your understanding of the weather equation and the material in subsequent blocks and modules.
The adiabatic chart graphically describes how stability works. Let's take a sea level parcel of air with a temperature of 22 degrees and a dew point of 3 degrees. If we lift the parcel, it will initially cool at the dry adiabatic lapse rate of 3 degrees per 1,000 feet, along the dry, solid red adiabatic lapse rate lines. A balloon represents our parcel of air. When the parcel is lifted, the actual amount of water vapor does not change. However, its relative humidity increases and the dew point temperature changes, but at a much slower rate than the decrease in air temperature. As the parcel rises, the dew point decreases along the mixing ratio dashed green lines. When the dry adiabatic line intersects the mixing ratio line, temperature and dew point are equal. The parcel has reached saturation. This intersection is the lifted condensation level, the level at which a parcel of air lifted adiabatically would cool and become saturated, the level at which clouds would typically form. Since condensation is a warming process, heat is released. This adds heat to the air and partially offsets adiabatic cooling. As the parcel continues to be lifted, it cools at the slower, saturated adiabatic lapse rate, represented by the small dashed blue lines. If we continue to lift the parcel to 15,000 feet, its temperature will be minus 12. The temperature and dew point remain the same, relative humidity 100%. Moisture has decreased, released through the process of condensation. When saturated air sinks, but contains no visible moisture, it warms at the dry adiabatic rate. Relative humidity decreases as the air warms. If we return our sample to sea level, its temperature will be 29 degrees. Following the mixing ratio, dashed green lines, its dew point is minus 6. This process explains hot and dry downslope winds, such as the Santa Ana of Southern California and the Chinook along the east slopes of the Rockies. A parcel is absolutely stable when it resists vertical displacement, whether saturated or unsaturated. The existing lapse rate is shown as the solid red line. If a parcel is forced upward, whether saturated or unsaturated, it remains cooler than the surrounding air. As a matter of fact, as long as the existing lapse rate remains in the shaded area, the parcel is absolutely stable. Since the parcel is cooler, denser than the surrounding air, it wants to sink. Thus, upward vertical motion is impossible unless caused by an external lifting force. An inversion, an increase in temperature with height, often exhibits the properties of a stable lapse rate. An inversion strongly resists lifting and in many cases puts a cap or lid on weather. Air is absolutely unstable when vertical displacement of a parcel is spontaneous, whether saturated or unsaturated. The existing lapse rate is shown as the solid red line. If a parcel is lifted, its temperature is always warmer than the surrounding air. The cooler, denser air surrounding the parcel forces it upward. Vertical motion is spontaneous. In fact, as long as the existing lapse rate remains within the shaded area, a lifted parcel is absolutely unstable. The atmosphere is dynamic. Depending on conditions, the existing lapse rate may contain both stable and unstable regions. In the photo, the lower layer of the atmosphere is stable, shown by the stratus clouds. An unstable region exists in mid-levels, indicated by altocumulus castellanus and virga, variable intensity rain gradient aloft, rain that evaporates before reaching the surface. Under certain conditions, the structure of a column of air can produce free convection if saturation occurs. Conditional instability. When the atmosphere is conditionally unstable, a lifted parcel remains cooler than its surroundings as long as saturation does not occur. This is like the stable situation described earlier. The point at which the parcel becomes warmer under these conditions is known as the level of free convection. If the lifted parcel becomes saturated, it can, at some point, become warmer than its surroundings and rise spontaneously without an external lifting mechanism. Conditional instability occurs when the existing lapse rate lies between the dry and saturated adiabatic rates within the shaded area. Generally speaking, dry air in low levels and warmer air aloft favor stability. High moisture content in low levels and cooler air aloft favor instability. If you haven't quite got a handle on the difference between vertical motion and stability, this should help. Convection, a low-level vertical motion producer. The clouds have little vertical development, indicating stable air. Convection has caused the air to rise to the lifted condensation level. Clouds have formed, but because the air mass is stable, cloud development stops at the top of the convective currents. On the right, convection has initiated vertical motion. Even though convection, the initial lifting mechanism, has ceased, the clouds continue to develop spontaneously in the unstable air. Upslope, an upward vertical motion producer. Cumuliform clouds indicate moisture and low-level instability. Since the layer aloft is stable, cloud tops will not exceed the upper limit of the upslope lifting. On the right, cumuliform clouds have developed because the atmosphere is conditionally unstable, and upslope has caused the air to reach a point where it is warmer than its surroundings, the level of free convection. The air is now unstable. Upslope, the initial lifting mechanism, has combined with sufficient moisture and conditionally unstable air to produce thunderstorms. How can we determine the stability of an air mass? Like moisture and vertical motion, a description of atmospheric stability is often found in National Weather Service Forecast Office area forecast discussions. The Upton, New York area forecast discussion alerts users to the possibility of an unstable air mass. The forecaster states, have removed CB appendage from previous TAF package. If the warm front does not move north during the day, and we are able to get some sun to destabilize the atmosphere, then there could be some thunderstorms around, just not very confident on where, when, and even if they will happen. Operationally, we'll keep a close eye on this weather event. Check METARs for frontal progress and any indication of convective activity. Be alert for forecast amendments. Check TAFs at scheduled update times. Throughout the series, we'll build on this discussion of stability and its effects on aviation weather.